yours.
Well, thank you so much for the nice introduction. I can see that you studied. I mean, remember everything. It's amazing. Well, hi everyone, and thanks also to the program committee and the program chair to have invited me here. It's an honor for me. I'm very happy. So yeah, as Renee said, I've been almost 10 years at NASA Langley, and there I worked on applying formal method techniques to aerospace software, and I recently joined a startup. So during this talk, for most part of it, I'm going to show you how interactive theorem proving has been used and combined with other formal methods techniques at NASA for analyzing and proving the reliability of floating point programs. After that, I'm going to show you a brief overview of how interactive theorem proving is used at NASA Langley, which is heavily used. And finally, I'm going to give you a brief introduction of what I'm doing now for Code Metal. So I'm going to show you what I plan to do. So use interactive theorem provers and also automated one for checking the results of LLM-guided transpilation, but also how ITP or ATP can be very useful to this problem, but also how it's the opposite. So how can we use AI, machine learning, LLMs for the ITP context? So let's start. So every time we write one of our programs and we write, for example, a constant such as, I don't know, 0.1 or 0.3, etc. What we have really in our mind, okay, we think this is what is going to be represented in my computer, right? So this is like a kind of a trick, because sometimes you write using base 10 and using numbers with comma, but actually what happens behind the scene is that these numbers are finitely represented in a finite amount of bits. So we can use either fixed point or floating point, and floating point is arguably one of the most used finite representation of real number in computer science. So being a finite representation, of course, not all real numbers can be exactly represented as a floating point one. And this is a typical example. For example, 0.1 is not a floating point, but instead is this number that is can be represented with this fraction over here. So every time we use a constant or we perform an operation using floating point number, we are introducing what is called a round of error. And a round of error is defined as the difference between a real number and its finite precision representation. So to give you an idea of how floating point numbers are introduced and may quickly propagate in our programs, I'm going to show you this example. So I think we can all agree that this is 0, right? Well, if we evaluate this with double precision floating point numbers, floating point arithmetic, we get this number here, which is a small number very close to 0, right? It's good enough. All right, then we compute the floor of it, and then we get -1. So this is already a divergence of 1. And then imagine that you also you check if this is negative or with a conditional. So you get a result of 100 when in your mind this will evaluate to 1, because in your mind you have real number arithmetic representation, right? So I hope I convinced you that floating point behavior is difficult to predict in general. And nevertheless, floating point numbers are ubiquitous, so they're everywhere, everyone using it. And not that recent, but in 2018, this study came out. And do developers understand IEEE floating point? Well, you'll be surprised, but many developers do not understand core floating point behavior particularly well, and yet they believe they do. Yeah, so of course, it's not surprising, of course, because we have maybe real arithmetic in mind, but we have all this nice property, we have associativity, commutativity, but this does not hold when we are reasoning with finite precision representation. Here we can have rounding error, overflow, and underflows, etc. So While floating point errors may be okay if you're writing maybe your small software and maybe you're in a domain that is not safety critical, but they can be very, very dangerous if a numerical error happens in safety critical applications. And I wanted to show you like the two prototypical examples that we always see in formal methods conferences. The first one is a pattern missile failure. Anyone knows about this? So what happened in 91 during the Gulf War is that this system that was used to intercept incoming missiles had a flaw. There was a numerical one because in the software they used the constant 0.1 to compute the window of time that was used to check if an incoming missile was coming toward the US base. So the 0.1 round of error may be very, very tiny, but if accumulated in many, many millions of iterations, it became that big that the window was computed incorrectly, so they failed to detect a missile that was incoming. And unfortunately, that was a tragic consequence of 28 soldiers dying and 100 injured. So this was a rounding error problem. And the second one, also a very infamous problem, was the Ariane 5 rocket. So in this case, Ariane 5 launched in the space, but it exploded after a few seconds. And that was because of an overflow caused by the conversion of a 64 bits floating point into a 16-bit integer. So luckily, no one died, no one got injured here, but the financial loss was very big. So 370 million US dollar were thrown away because Ariane 5 exploded. So we don't want this. So we want to check programs before this happens. So more recently, we also discovered in a more recent example like numerical flaws in a standard called Automatic Dependent Surveillance Broadcast, or ADSB. So I don't know if you're familiar with this, but ADSB is part of the next generation of air traffic management systems that's going to enhance and maybe in the future also replace the radar. So how it works, ADSB, the aircraft periodically send information via message to all the aircraft that are around and also to ground stations. It's automatic, so no pilot intervention is needed. So this system broadcasts any thought number of seconds the information, and it's mandatory, at least in the US and in Europe, since 2020. So now there are thousands of aircraft that are equipped with ADSB, even the one that maybe you came to Iceland with, I'm sure of it. So the good thing about ADSB is that it provides more coverage and is more precise than radar. So do you ever use Flight Radar 24? Maybe. So when you see in Flight Radar that your aircraft is here, that is not the real position. That is a projection. The radar doesn't reach that part in the middle of the Atlantic Ocean. That is a projection of the position based on the last information that has been received, that is the direction, the altitude, and the velocity of the aircraft. So yeah, with ADSB, we don't have this problem because we are broadcasting the information. The bad thing about it is that they wanted to use existing hardware, which is TCAS, which has a fixed number of bits for the message. I think it's 58 bits for the message, of which just 35 are available for the latitude and longitude of the aircraft. And if we translate it in like row position, this is about 300-meter precision or granularity, which of course is not enough for safe navigation. So in ADSB, there is this key algorithm that is used to encode and decode the position so it can fit in these 35 bits. So we only have, if we divide by 2, we have only 17 bits for latitude and 17 bits for longitude. So the idea of the people who developed CPR was this is like a very high-level overview, but imagine that we have a new system that is composed by zone, which is equally sized. And we have either 60 or 59, depending on the kind of encoding we are using, that we will call odd or even. And then each zone itself is divided into 2 of the 17 bins. So we have only 17 bits to represent the position. We divide the bin into the 17. So we're going to use that information. So a position is going to be determined by the zone number plus the bin number with a precision of 5 meters, more or less. So how it works. So the CPR encoding is very easy. This is the latitude encoding, for example. And this computes the bin number for the latitude, which is going to fit in 17 bits. And only the bin numbers are transmitted, not the zone. So this is how the message is composed. We have the kind of encoding that has been used. So if we divide the Hz in 59 or 60 zone, and then the bin number for both dimensions. And you can ask now, oh, we only have the bin number, so how we retrieve the zone? So CPR have two ways of doing this. One is called local decoding, which uses a previously decoded position, which is sufficiently close to the time where the new message has been received. Or it uses a pair of messages that has been sent sufficiently close to each other, and one odd and one even. And it uses like an algorithm similar to things called the Chinese reminder theorem. So it counts the number of zone offset that are in the difference between the two messages. And then in this way, it can univocally retrieve the zone number. So what's the problem? So when they started to use this algorithm, pilots and manufacturers started to notice very strange things happening. So this is a situation reported by Air Services Australia, where the actual position, the difference between the actual and the decoded position was about 241 nautical miles. So that's not a small error. So at NASA, we started to, in collaboration with FAA and Federal Aviation Administration, we started to look into this problem and this algorithm. So the first thing we noticed and we found is that the requirements were not enough to guarantee the safe behavior of the system. So we proposed a slightly tiny set of requirements, and they were all related to the fact of sufficiently closed. So that has to be tightened a little bit. And then we proved in PBS that the algorithm, assuming real number arithmetic, was accurate. But what about finite precision implementation? So as you notice, this algorithm uses modulus and floor. Modulus and floor, we see at the beginning of the presentation, are highly unstable. So we have a huge accumulated round of error because of them. This is an example we found while testing the algorithm, that using single precision floating point, we found one case in which we have a 1,500 miles difference. So that was so what was our approach at that time? We proposed a simple formulation of CPR that reduced the numerical complexity. So we redefine everything. And then we use a suite of existing formal methods tool to provide proof that this new version is correct and also does not have rounding errors. So for this, we use FRAMA-C, which is a static analyzer for C. It's very popular. Theorem prover PVS and GAPPA. GAPPA is also a prover for numerical programs. So this is an overview of the approach. We have here, this is the ADS-B standard. And from that, we have the original real value specification for which we have provided a proof for this slightly different set of requirements. Well, first of all, at NASA, we had the expertise for using PVS. It has been used there for 4 decades, and there were like many theorems that we have already, ready to be used that include, floating point theorems, algebra, analysis, etc., etc. So mostly because like we had in-house experts. But also, you may have seen this movie. So PVS is the only theorem proven, and prove me wrong, that has been featured in a Hollywood movie. So if you if you watch The Martian, at a certain point, you will see like this. And this actually, I don't think this could have really helped Mark to go back to Earth, because this is the formalization of Bernstein polynomial in PVS. We don't know how the people like doing the movie choose that one. Probably like it was random, but yeah, that is PVS, and it was very funny when we found out. However, PVS has also a connection with real Mars missions, and it is used for in this tool called Plexil 5. So Plexil is planning, a planning language that is also used in Mars rovers, and there is a formalization in PVS. So not that far from reality, right? So yeah, so we, as I said, like going back, so we have this new algorithm that we call CPR star that has all these numerical simplifications, so it's more numerically stable, and we have proved it correct for both double precision floating point and fixed point 32 bits. And now this is the reference implementation in the ADSB standard document in the new appendix. So like manufacturer now can look at that. And also that was cool. We got a NASA achievement award for this, which was very nice. But while this was a successful combination of different formal methods tool for a real world problem, the thing is that it requires so much manual effort. So nothing was almost automatized. We have to manually annotate the C code. GAPA needed hints for verified tight round of error bounds. So we have to tell GAPA subdivide the domain into these intervals to get this round of error. A lot of time and effort was spent proving the 2 version equivalent in PVS manually. So it requires a lot of expertise both in theorem proving, but also in floating point arithmetic. So we wanted to, step by step, make this process fully automatic. So when we started to work on floating point analysis, we wanted to have 3 things. First of all, we wanted formally verified and sound bounds. So we wanted to have an externally checkable certificate in PVS or any theorem prover. We wanted some treatment of conditionals. So in the example I showed you at the beginning, we saw how conditional can really throw off the computation in floating point, and we want it to be accurate. So during the past 20 years, like floating point analysis, or in general, like the research in floating point and fixed point has been very active. There's been so many tools, not only for floating point analysis, but also for floating point tuning. So deciding which are the best precisions to use in your program to also obtain certain an optimization in terms of time, execution time, and floating point optimization, for example, to find the best rewriting, the best rewriting that makes your arithmetic expression more numerically stable automatically, etc. At that time, we are here. So there were a few already present GAPA, which was used in the CPR problem we had. So it was good, but it requires a lot of manual effort to get tight bounds. Otherwise, you would get like very coarse approximation for the round of error. There was Fluctuat. That is a closed, it's not an open source tool. It's commercial, and it uses abstract interpretation behind the scene, an abstract domain called it's Xenotopes, but it didn't produce any certificate. So okay, it's abstract interpretation. We know it's correct by construction, but we also wanted a certificate. There also may be some implementation mistake. And there was this VC float that I had also based on interval arithmetic with proofs in ROC, sorry. And Sorry, you have to get used to the new name. But it wasn't accurate enough. So Precisa came in 2017 at the same time also FP Taylor, which is very cool. It uses Taylor approximation for the round of error, and it has proofs in whole hike came out, and then there was Daisy, also using whole, VC float. It's a new version of VC float 2, which is a new version of this using rock, etc. So many tools available now. And so how does Precisa work? So the input is a floating point program, and the output is a round of error that may occur in that program, plus a certificate that can be externally checked in PVS. This is a high-level description of how Precisa works. This is the workflow. So as I said, the input is a floating point program. Then we perform a static analysis also. It's based on after interpretation, but it's all symbolic. So we obtain a symbolic error expression that does not depend on any input ranges. Then we take this symbolic expression and input variable ranges for the variables, and we optimize it through a branch and bound algorithm. And we obtain a round of error bound. And at the same time, we also generate certificates that can be proved in PVS. At the beginning, these certificates were proved by hand. And also, after that, we have implemented automatic strategies or tactics, as you want to call it, to discharge it automatically. So let me go into a little bit more detail on each of these 3 steps that we have. So the first one is static analysis. So what we are computing for each function declaration in Precisa is a set of what we call conditional error bound that contain all the information you need to reason on the round of error. So we have conditions. As I said, one is on the floating point and one on the reals, because we want to be accurate for the conditionals in our program. So we want to distinguish when we have these divergences in the flow. Then a symbolic expression, which is the real value of our function, and also symbolic expression, which is the round of error. And everything is symbolic, as I say, and it's compositional. I want to mention that this can become huge because everything is symbolic, so we are using abstraction to mitigate the state explosion. And yes, and the condition on the real and on the float are kept separate, because in this way we can take into account of this conditional instability of anything else. On the step 2, we get the symbolic expression. In this case, it's very simple and bounds for the variables, and we maximize it with a tool. It's called Kodiak. Kodiak is also a NASA tool, and it performs a branch and bound optimization which is parameterized with respect to maximum depth and precision. So we have both a C implementation, which is very fast, and we also have it in PVS, which is formally verified. So we use Kodiak, the quick one, for computing the bounds, and then we use the PVS, the slow one, to check them. In PVS, we have defined whole the theory of floating point and the theory of round of error. So this is an example of formalization of the bound for the multiplication. So in our model, we have the round of error is composed by 2 parts. We have the accumulated round of error that come from before, and then the rounding of the operation itself. So we have 2 separate components. And yeah, you can find also in GitHub the IEEE 745 and 85. Sorry, I made a mistake here. 854 in GitHub, in PVS, if you're interested, and also the Precisa tactics or strategies. A thing that I forget to mention is that we're assuming that IEEE standard, so every operation is implemented as if it was computed with infinite precision and then rounded to the nearest floating point. So this is like our assumption, and like many implementation of programming languages must follow this. For example, C. And at the end, we produce this certificate This is just an example, but we can see we have, in this part here, we have the input ranges. This is the post condition, so that the difference between the floating point program and the real one is at most this rational. This part here, this two line is mimics basically that we are following the IEEE standard, but yeah. And this part calls the tactic. So Precisa has also a very nice graphical user interface, which is integrated in VS Code. That makes it a little bit easier to use and also perform some analysis with different input ranges, sensitivity analysis, comparative analysis with maybe two different implementation of a same algorithm, etc. And this is my favorite part of the graphical user interface, which is the instability analysis. So if you remember at the beginning, I showed you how easy you can take the else branch instead of the then one or vice versa. And this part of the tool, what it does is perform with a Kodiak paving functionality. It paves a 2D space, so you can see which values may provoke the instability. So that is pretty cool. Oh, also, it can tell you that everything is okay. You don't have instability. So at this point, I think you are all convinced that real numbers are not floating point numbers, or better, the opposite. Floating point numbers are not real numbers. So what happens if we are in ROC, in Hall, in PVS, we have our algorithm, very nice, we prove property on that algorithm, we're happy, and then we implement it, and these properties do not hold anymore because of all the things I told you before. So wouldn't it be nice to have a code extraction from, for example, our favorite theorem prover into a real programming language that we can run fast, like C? Well, yes, it would be nice. And that is what we have implemented with our other tool called Reflow. So Reflow takes as input a real value specification of an algorithm and produces a floating point implementation in C, annotated with pre and post conditions that specify how the round of error accumulate. And to do so, we use, of course, the other tool Precisa to get the round of error bounds, and that are proven in PVS. So this is an example of the code that is extracted, which is annotated, which is huge. I know, even for this small one, this small function, but it's a nice example because it's simple. So this is called EPS line, is a very simple function, which is in our library called Daedalus, which implement the minimal operational performance standard for drones, UAS. So in our annotation, we will have, first of all, the axiomatic real value program, which is this one. So it's the same one, but with reals. Then the floating point implementation. We will have initial ranges for the variables. The variables are round to the nearest, as we said before. And finally, the post condition, so that the result minus the result in floating point minus the result using real numbers is at most this number here. And what happened when we have if then else? Well, Reflow also implement what we call a code instrumentation to detect unstable conditional. So every time we have a conditional and it uses floating point arithmetic, we basically what we do is replacing it with a new if then else with guards that are stronger and take into consideration the epsilon or the error that may occur in the guard. So in the case the guard may be evaluated differently in floating point or in the real, we will get a warning. And finally, this is the part where we use from a C. So we have our annotated program. This can be input to from a C. From a C gave us some verification condition. This time, we have implemented a framework for the verification condition to be in the language of PVS, so they can integrate also with the certificate that we get from Precisa. So it was like the whole overview of the Reflow work. And we have a couple of applications of reflow. One is for Daedalus, the unmanned aerial vehicle standard, and the other is for geofencing application, a library called Polycarp. Basically, it tells you if an airplane is inside or outside a given polygon. So it was like the overview of how we use ITP and formal methods in general for floating point analysis. However, interactive theorem proving at NASA, Langley especially, is widely used in a variety of applications. So these are a few examples. So we have, okay, I already talked about Daedalus. Daedalus is also formally verified and completely formalized in PVS. Icarus, it's another, it's an extension of Daedalus, which is also defined path planning, and it's configurable for different kind of UAS. This is Platypus. No, it's very cute. So this is an implementation in PVS of the differential dynamic logic, which has been completely formalized, and also you can interact with it. And we have extended also it with temporal properties. And then what else? Oh yeah, we have requirement elicitation tools like FRET that also has the, FRET is a natural, kind of like natural language formal, well, I will say that is kind of resemble natural language, and it is used for defining specification, temporal specification. And it has been implemented at NASA Ames. So since FRET generate LTL formulas, we have proved that the semantic of FRET and the semantic of the formula that is generated is the same, so always also using PVS. And finally, I already talked about the Plexil 5 and Mars rover application. So yeah, it's still used a lot. And if you have questions about all this, let me know, and I will point you to the correct person at NASA that works on that. So this is like my past while I work at NASA. I was there for a long time, and I have recently joined this startup called Cold Metal. So I know, like, when in this programming language or formal method setting, it's a little bit, every time we hear the word LLM, we're a little bit reluctant. But what we do is LLM-guided code transpilation for edge computing, but in general for code modernization. So this is the diagram that they allow me to show you. We have some reference code, which is, and then we want to transpile it, also with the help of LLMs and with the help of verification. And then we want to optimize it for a specific hardware. Okay, we all know that LLMs are black boxes. We cannot verify them with traditional formal methods. And also we know very well that LLMs can hallucinate. We don't want to trust the result, because if we ask, I mean, even if you vibe code, right, you can get something sometimes that is not really correct, and you can be surprised, but this is because how LLM work, they can hallucinate. So we can have semantic discrepancies, code that contain vulnerability, and also some violation of some specification. So in this context, of course, we want to use formal methods for checking and make sure that the code that is generated with the use of LLM is actually good. So it's semantically equivalent to the reference code. It doesn't have code vulnerabilities, and maybe also we may be interested in some compliance with standard. For example, in some industry, it's important MISRA C or MISRA C++. So, of course, formal methods can be, are very useful and are essential, in my opinion, when you have this kind of structure and you want to use it for code modernization or even for code generation in specific industry, especially. So LLM generated code must be validated and verified. So here we are not talking about vibe coding. We are talking about taking an entire library and have the transpiled version. So it's not interactive process. So here our source, our input is a source program, which is our specification, our oracle, in a language. In this example is Python. Then we transpile it, and maybe we get a a program in our target language, can be C++ or C in this example. And we can use many formal methods or not formal methods technique to check that this program is correct. We can use differential testing. We want coverage information. We want formal verification, and also static analysis, of course, especially if we want MIS-ROC compliance. How are these methods integrated? Well, we call these like tools to check different properties, tests, etc. And also we have implemented repair loop, as they are called. So we use the result of formal verification testing and static analysis to do a feedback back to the LLM. So LLM can help both. LLM can alleviate. What I want to say like here is that ITP or formal methods in general can help getting better code, but also many times we want to use formal verification. So as you may know now, there are many techniques that try to use LLM also for generating proof, etc. And I think this is a good thing actually, because in this context, it's not like in here that you have a program that you have to verify, and it's kind of like a little bit more difficult. Like if we generate a proof, we have a direct way to verify it right away. So it's not like I won't say that it's a bad thing that we use LLM for that. And it actually can be useful to get people to use more interactive theorem prover in general, because it really reduces the time you spend doing the proof. And sometimes people are scared of seeing like a lemma or a very big proof, and it can be a little bit overwhelming. And I think that LLMs in the future can help like people get a little bit more acquainted with interactive theorem prover and their value and to see their value more and more. So yeah, we can discuss about that. I know that recently there has been many papers using LLMs to do different kind of tasks for interactive theorem proving, and I think that's great. So yeah, in conclusion, I'm very early. I think I talk very fast, but that's good. We can discuss. So interactive theorem proving are still very used at NASA for safety critical application. So I show you some examples before. And ITP can also be very beneficial in the industry, especially now that we have a lot of LLM in the midst, and it's used by a lot of software engineering. It can introduce error. We know that it's used. So it's good to have a formal proof. But also, ITP can benefit also from LLMs or AI in general. So we can think about, well, this is a dream, right? Proof translation for across different platforms. Wouldn't it be good to be able to take a library in PVS and translate it to ROC, for example, like doing the code translation, but with proofs? That would be cool, I think. We can have code repair transpilation, code repair simplification. So it had happened many times to me that I was writing a proof in PVS, and you ever get so frustrated, you just want to get over with it, and then maybe realizing in the middle, oh, I did already this. I should do a lemma, and maybe call the lemma, but I don't want to do it now. I just want to get over. And then I have a big proof, and maybe with some repeated stuff all over. So wouldn't it be nice to have also like a way to simplify, like, hi, this is the proof. Can you maybe reduce the size, simplify it as much as possible? But in PVS, there's no way to do that. I don't know if in any other theorem prover there are. Or also we can, of course, proof generation and automation would be another thing that LLM can be used for. So I think there are exciting research topics to be explored at the intersection of ITP and AI in general. I think we all agree on that. And I think that the main difficulty here is there are not many people that are expert in both things yet. And also the community have been very separated until now. So I think that is something that's going to change in the next few years, in my opinion. So, and I think that there were magic happen, or like the good things will happen in this when we really have this cross-contamination between the two research areas. So yeah, that was it. I want to conclude, like, this was not done just by me. All I presented, the first part, the NASA library, etc. I have to thank all my colleagues at NASA, and also for the work I'm doing now at ConMetal, my colleagues there. So yeah, this is my email, and if you want to reach out if you have any questions or in the future. Thank you.